So today we're going to go into using MPI. We're going to talk about some of the things that you should be thinking about when you're designing codes and when you're trying to figure out how to make them faster or how fast they should be. And we're going to break this up with some exercises, so we're not going to be lecturing for the next 8 hours. And one of the first things I wanted to talk about is the cost of unintended synchronization. And we saw this, in fact, yesterday in the discussion of vectorization for individual nodes. It's that when you write a piece of code, you may say stuff about the order in which it executes that is more than you intend. And so some of the examples of code that would not vectorize was because the code as written in the language had certain requirements on its execution that effectively serialized some of the activities, meant that you couldn't vectorize, that you had to complete one operation and do the store before you could do the next one. The same sorts of things happen in MPI, and it's very easy to do that. And so I'm going to show an example. So I think it's interesting because I believe this example is from code that is older than some of you. Certainly older than, or was written before some of you were in kindergarten. As we look at some of these simple codes, you can get surprising performance out of them. You can get kind of performance that you may not be expecting. And I'm going to show an example in the next couple of slides where you can get this with even a very simple grid exchange pattern. So you have a stencil operator, you do the exchanges for the ghost points, and we'll talk about all of that in a little bit. I want to also emphasize that the sorts of problems that I'm going to show are not because it's message passing, it's because it's parallel. So if I was doing this with co-array Fortran or UPC or Chapel, I would see the same effects. And in fact, they might be worse in some cases. So here's the example. I've got a mesh. I'm going to think of it, a single two-dimensional mesh. And it's been divided up onto 12 processes in little rectangular patches. And it's a very simple stencil. So it's there's an operator here that requires, let me take this one here. There's an operator here that requires the point to the immediate right, left, up, and down, often called a 5-point operator because that's 4 plus the one at the center. And that means that for a point that's at the edge of this domain, it needs a point from the neighboring domain. So we typically send the data back and forth. It's a very sort of simple pattern. Okay. Well, this was a long time ago. People who wrote the code thought, well, maybe we could do this. It seems like a fairly simple code. I've got the data that I need to send to my neighboring process. There's a certain amount of data. I can send it, then I can receive it. Okay. Now, is there any problem with this code?
Everybody's got to send before they receive.
Yeah, everyone has to send before they receive, so it may deadlock. And then I do say may, because it depends on how the MPI implementation implements the blocking send. So the code might work, or it might work for a while until you've gotten a lot of confidence in it, and then you make the problem bigger, and it suddenly deadlocks. Well, the first thing you can do is say, OK, I have to make sure that there's some place to receive. So you can say, for example, if there's a neighbor below me, and I'm thinking of this just as a one-dimensional decomposition, so say strips, then do the send. And if it has a neighbor above me, then do the receive. Now, this may be the worst possible code. I say worst possible code because it works. It won't deadlock. It will complete. But it will be completely serial. So we'll look something like this. Each process will start sending, except for the last one that has no immediate neighbor, who will do its receive. That receive will cause this send to complete, which will then allow that process to start its receive. And you'll get something like this. And so the code will run fine. It just will have completely non-parallel communication. And so one of the lessons is right here. And you've, again, I don't know if it was made quite as explicit as I'm about to make it yesterday, but it was through every single presentation that you saw yesterday, is that you need to have some sense of how fast the code should run so that you know when something is wrong. And that doesn't have to be a very accurate sense. I'm not saying if you don't get the prediction within a %, you failed. No, I think factor of 2 would be fine. After all, this is a p-fold slowdown in communication. And there's a lot of room for approximation here. Right? So you need to have some sense. And in fact, the research group that sort of stimulated us to look at this had done the right thing. They had written this code. They had gone through these steps. And they realized that the code was not running as fast as it should. And that puts them ahead, frankly, of many, many of the groups that we talked to who have no idea of how fast it's going. Where a lot of what Torsten talked about yesterday was that it is possible to know, and at various levels of detail. So even a log p sort of model, and I will say a log p model is actually not going to be adequate for what we want to show here. But even a log p model would suggest that something was wrong. OK, so here's a fix. Say, OK, well, those things blocked. We know that we don't want to block. So what I'm going to do is I'm going to post all my iReceives. And then I'm going to do these sends. Right? So not iSends, it's sends. So the thinking here was, OK, I have to avoid this serialization. So I will make sure that all the receives are posted. And that means that I will have to do this wait later. And then I will send. And OK, so that seems fine. It's not going to block. These sends will all proceed in parallel. Now, if you're thinking about the blue gene, there's another reason why you might not want to do this. Let's hold on that. I will get back to that. But for the machines that they were looking at the time, they could send essentially to one neighbor at a time. They didn't have 10 separate engines. They had one. Okay, so this seems like a reasonable way to write the code. But they found that it didn't perform as well as they thought. And again, that's because they had some sense of how well it would perform. And the sense that they had was basically you do how many people know what a ping pong test is? Okay, that's some of you. So a common test for message passing systems sends a message from one process to another and then back. So ping, pong, and measures the performance of that. And then you get a latency, which is let's say the lim-inf of the time that it takes to send data, smaller and smaller data back and forth. And you can ask me at the break why I'm being so weird about that definition. And then in bandwidth, which is roughly the rate at which you can send very large messages. So you can use that and figure out I've got so much data that's being sent. I have a bandwidth. I can figure out how long it would take. And then they observed it was taking significantly longer than that. OK, so let's try to understand why that was happening. So I'm going to assume that the sends interleave so that the data proceeds out to the different destinations. The sends do block. So I can't start the next send in this example here. I can't start the second of these sends until the first one completes. Receives don't interfere with the sends. And in that case, there are 4 neighbors. So this thing can be done in 4 steps. Okay, and my unit of time is going to be a step, as if I was sending the data. So let's see what really happens. Okay, so in the first step, so this process is sending down. So it can send down. This process sends down. This process sends down. This process doesn't have a down, so it proceeds to the next send. And the next send sends right. Okay, and this one sends down, this one sends down. Well, both of these are targeting the same process. So you get congestion. And I've dashed these. This is the sends interleave. I've dashed these to say that some of this send completes and some of this send completes because this process can only absorb sort of 1 unit of data. And it's receiving 1 unit from both of these. So it gets half from this one and half from this one. So it can only have gotten that half done. And the same thing happens here. And this process has no right neighbor, so it also has to send up. Okay, so all of these communications with the dashed lines only get halfway through in the first step. Okay, so now we go to the second step. Okay, well, so this process, for example, that it sent down can now send right. This process that's sent down can send right, and so forth. But this process that's sent down can send right. But this process that's sent down has no right, has no up, so it sends left. So again, this process is absorbing 2 units of data, 1 from each neighbor. So it only gets through half from each of these. And similar things are happening down here. Let's see, these processes are okay because first step down, second step right, they're done. Okay, this one is just finishing. It's not too bad yet. Now, step finished, it's right, it can do up, this one can do up. This one can do up. This one has no up, so it does its left. So this gets halfway through. These I dotted, and I'm going to be a little cavalier about this. This one's now absorbing from 3 directions. And so it's going to only get part of the way through this. This is step 4, by the way. Right? So I said that, if everything happened in lockstep, if I sent down, right, up, and left, at the end of step 4, I would be done. Well, note that like this process is just finishing sending up. Right? That was because it was delayed sending down because its target process was the target of another send. Okay. So that means there's a step 5. Okay, I'm already slower than I should be. As some of these processes complete, this one's still sort of dragging along. And there's a final 6th step where finally these 2 interior processes complete. So that's 6 steps instead of 4. That's a 50% slowdown. So they didn't have to have a very accurate communication model to find a 50% deficit. And so it's very useful to have some kind of a model. And we can look at this. So this was a plot that we did a long time ago on an early IBM parallel machine, the SP. And each of these blue bars here is a send. And they're all, in this example, they're all sending the same amount of data. The fact that some of the data is on a vertical edge instead of a horizontal edge, I sort of ignored. So there's no, everything is sending a block of contiguous bytes of the same size. And so in a perfect world, the send bars would be exactly the same length. Right? And what you see is that some of them are like short and some of them are longer. In fact, if you do a histogram of the length, you see that some of them are short and some of them are longer, and there's quite a distribution here, but there's definitely another pool of sizes. And again, if you go back here, you can see that. Here are the short ones. So those are the ones where there's no congestion. And these are the ones where there is congestion. And if you look at the rank numberings here, the completion times pretty much mirror the model that we've been through for this. So again, an important thing here is a very simple-minded model has told us a lot. Because we've thought about how does the data get from the memory of one process to the memory of another process? What does it go through? Where might there be contention for a shared resource. One of the reasons I said that you'd have the same thing if you were doing shared memory is in that case, the send looks like a mem copy. And mem copies are all blocking because they have to finish before you go on to the next mem copy. So if I was doing this using a shared memory model, I would run into the same sort of behavior. Okay. So in summary, that ordering of sends, that introduced a delay. It was an unnecessary synchronization because the code said, finish this send before you start the next one. Right? You didn't care. In doing the halo exchange, it's almost certainly the case that the code doesn't care in what order that data arrives. But as written, the system was mandated, had no choice but to fully deliver that first buffer and complete that send before it goes on to the next one. Okay. So that makes it inefficient. It wastes bandwidth. And as I mentioned, if you did mem copies, you'd have the same thing, because the semantics of the mem copy is it completes. Now, it doesn't start, it starts and finishes. One of maybe the biggest things to remember when you're thinking about parallel programs is that there's a big difference between when you start something and when you end something. And that's the case whether you're talking about single core performance and pipelining, and same as if you're talking about moving this sort of data. Okay, so the real fix here is, well, we have the same block of I receives here, but we changed this MPI send into an MPI I send. I mean, that's the only change. And then that gives us twice as many requests on which to wait. And this has a number of really beneficial effects. So the first is I'm no longer saying that each send has to complete before I can start the next one. So a suitably sophisticated MPI implementation can observe that data is being held up going to one destination. It will start sending data to another destination. Now, I was also very careful how I said that. I didn't mandate that the MPI implementation do that. Right? And in fact, you can imagine the following unfortunate circumstance. Inside the MPI implementation, it has a shared memory model, maybe a remote memory model. And so when it starts one of those ISENDs, it does it with what is effectively a remote mem copy. And if it really thought of it that way as a remote mem copy, it's going to wait till it finishes. Right? So it's not easy to do this, but your code should be exposing as much as possible to the implementation in terms of opportunities to reorder the delivery of the data. And again, it's really fairly similar to what you heard yesterday about getting, say, on-node vectorization. You need to expose as much as possible to the system. You need to give it as much flexibility in how it orders the execution of the, in those cases, the individual statements, in order to at least give it the chance to get good performance. Okay, in this case, what happened on that system was the system sends data in different packets. And so it would send packets for the message. And as there was back pressures, and couldn't push those packets out to one destination, it would start pushing them out to another destination. And so it pretty much looked like this, where you have data going everywhere for all 4 steps. Some of the processes, in fact, all the processes on the periphery here complete a little early because they've got a little less data to move. And that's what you see in this image here, which is the same computation, basically, that run the same day on the same machine. This time is now all the time that's spent in the wait. So that's where the data is arriving. And these two that are a little longer than the rest of these, they're maybe 25% longer. That's because they are, in fact, these 2 processes, the only ones that have 4 neighbors. Okay, so the lesson here is to defer that synchronization to, yes?
So can you go back to the I send and I receive? I just said that if I switch the order of I receive and I send, does it matter?
Yes, no, that's a good question. And the answer to which one is better is it depends. So since we have a little bit of time, let me talk through that. Okay, so this was a way that was the best way to write the code at the time that this example was done. The reason for that was that let's think about what happens when you when you execute code like this. In fact, let me think about what happens if I execute the code with the send first. Okay, so I do the I send. Well, what happens? The I send will, what's likely to happen is that the I send might send a message to the target saying, I have some data for you. And the target will say, I'm ready to receive it, or I'm not. If it's ready to receive it, it might say, go ahead and send it. Well, at the time that this was written, the threshold where the system decided whether or not to ask whether it could send or it would just send was actually quite large. And so that first code would in fact run even for messages of about 128K because that's what it would allow to send. So the send would just send all that data. It arrives at the target process. The target process looks at it and says, I don't know what this is. So, but maybe somebody's going to want it in a little while, right? So it's like you send something to a hotel before you check in. You know, they take it and it puts it someplace, right, in some storage room, okay? And then a little later, the I receive is posted. And the first thing it does is did somebody send me something that matches this? It goes and looks in its luggage room, and it finds his message, and then it copies it in. Okay? Well, you can imagine that's a fair amount of overhead. There's an extra memory copy on the machine at the time. The memory copy was, in fact, quite slow. So the approach here is post the receives first. That means that there's a good chance, if everybody's sort of on the same schedule, that by the time you call the I send, when it sends that, either sends the data itself or it sends the request to send the data, that the target's going to say, I know exactly where that's going to go. And then it might say, if it's been sent the data, we'll just plop it down in the right place. If it hasn't been sent the data, it may send back, well, in fact, if your network allows direct remote memory copy, it might say, I've got the place for you. Just do a remote put to this location. So, and then that would, it goes back to the I send, and then the data is delivered. Okay. So now, why might, I mean, that seems like then this is the right way, and there's no ifs, ands, and buts about that, right? So why did I say it depends? Well, in particular, say that I put some code in here between the I receives and I sends and the wait all. And let's assume that I'm sending enough data that it's not going to just deliver the data. It's going to wait for permission to deliver the data. So in this case, I post the I receives. Everything's local. The I sends send out requests to send. And that takes a couple of microseconds. Well, in a couple of you can do a lot in a couple of microseconds. So after a couple of microseconds, that entire loop is done, and it drops into the compute code. Starts computing. The requests arrive at the target process, and they sit there until somebody gets around to look at them. So, and then maybe in some implementations, nobody will look at them until you call the wait all. In other implementations, a timer might go off after a millisecond, or on the machine that we ran this after 470 milliseconds. And that's when they would look at it and say, oh, yes, you can have that data. If you do the I sends first, then those requests start filtering out through the network. When you do the I receives, there's a chance that the request will have arrived by the time you do the I receive, which will allow it to send back the yes, you may go. which at least will allow that part of the handshake to then overlap with the compute. So I hope this was not too grungy, but a fairly simple, this is a fairly simple model of what's going on, gives you some insight into what the trade-offs are. Right? Maybe another part of this is, I know a lot of people talk about performance portability, and then we all want to write one piece of code that will run everywhere. Who does not want that? Okay. Who thinks you can do that for any piece of code? Excellent. Let me point out for those of you in the front that nobody behind you raised their hand either. Right. I will point out that if we could do that, there would be no BLAS libraries because you would just compile the code. It is too hard. So given that, what do you do? Well, you have to start thinking about organizing your code so that you don't commit yourself to a particular strategy because you may have to change. And again, one of the nice things here with this code arranged like this, it's very easy to change the communication strategy. Right, there are other things that I can change here. So for example, the order in which I send these can also matter. For these simple examples that we're doing where you have 4 neighbors, pretty much doesn't matter. For some of the more sophisticated examples that you might be doing for your day job, you might have 30, 40, 50 neighbors. In that case, it can matter. Because if you think about it, what happens? Message arrives, it's got to be matched. Well, how's it going to do that match? It's got to look through everything that's there. And if it's looking through 3 things, right, that's like looking on a shelf where there's 2 or 3 things. You can just pick it up. If there's 40 things, it's like opening a jumbled closet that you have to start rooting through to find things. And you will see those effects as well. So then it can matter exactly how you order these things. OK. Any other questions? OK. OK, so back to this. So it's really valuable then to be thinking about this, to have a model. Remember, none of this would have happened. We wouldn't have gotten this example if the team that was doing the code didn't have a simple model for how fast it should be. Otherwise, they would have just been happy and their code would have been slower than maybe somebody else's and nobody would have known. Maybe nobody would have cared, but they would have gotten less work done because the code is running artificially slow. So have a simple model. I want to say, we've already gotten a couple of questions about I/O. This is probably the place where the situation is both the worst and possibly the best, is that in many cases, the performance that codes are getting on I/O is orders of magnitude below what they should be getting. And they may not know, they just know that things are slow. And they want a faster I/O system. But in many cases, it's the analog of this, that their I/O has imposed certain synchronization requirements that they may not know about, but that the language requires. So how many people know about POSIX I/O? OK, just a couple of you, sort of. And do you know the syntax or the semantics? Or do you know what I mean? So the syntax is how you write something. So in POSIX I/O, I can use open, close, read, and write. And there was a time when system says, oh, we have POSIX I/O, when they meant they had this syntax. The semantics is what happens when you do a read or a write. When I do a write, what happens? Does data go someplace? POSIX has extraordinarily strong synchronization requirements. So in particular, when a write completes, any read executed anywhere in the known universe that came after that write must see the data that was written. This is, in fact, not possible in this universe because it has a sense of simultaneity. What it does is it forces data to be, the implementation is usually done by forcing the data to be written out to disks, so the next thing that tries to read it will then read it from disk, which makes it almost impossible to effectively cache data. Those of you who have used faster parallel file systems and if gotten a message saying the system is down for a little while we fix a parallel file system? How many people have gotten one of those? Right? Yes, now lots of hands go up. The reason you've gotten those is the parallel file system is trying to work around that problem by doing very careful strategies to try to cache different kinds of data. It's really hard, and they don't always get it right, and that's when things break. So it's another place where you might have a synchronization that you don't even know about because you don't think about it. You say, I wrote the data, I don't care. I hope it appears someday. Right? But to the library, to the language, that has a very different meaning. When that write returns, everything's done. That's not probably what you want. And so there are ways around that. But you have to, first you have to know that you're facing that kind of problem, that you're not getting the performance you expect. Then you have to know what does the language, what does the library require, and finally how to get around it. So we'll see some of those examples over this week. We'll look at some of these for the simple neighbor exchange. And with that, in fact, oh, and I wanted to say one other thing. One of the things that I think is really nice about this sort of era in parallel computing is we're discovering as we need to change things. Okay, so that's bad. It means you have to rewrite your codes, right? What we're discovering is that there's a couple of common ideas that help you solve multiple problems. So we've been talking about, Pete in particular is talking about the fact that performance is no longer as predictable on these systems. That means that you need to be more dynamic. And if that was it, that would really be unfortunate because it would mean that you had to restructure these codes because of this one fact. But it turns out that more dynamic codes give you much more flexibility in many different dimensions. Right? So more dynamic here helps deal with this, not just local performance irregularities. It helps deal with remote performance irregularities. It also helps deal with the fact that even when you tell somebody I have exactly the same work on every thread, you might say, well, what about the boundary conditions? Oh, yeah, the boundary conditions aren't exactly identical everywhere. There's always some little differences. So the same thing here. Moving away from the synchronization is good. And the example here is that for BlueJean is really cool because instead of trying to have one honking fast communication channel, which is a little easier to write this sort of code for, it has 10 pretty fast communication channels. But that means that to get real performance out of the system, you've got to use them all. Each one you don't use is just lost performance. You know? The same comment as if you want performance out of your code, you've got to vectorize because that's where a lot of the performance is. If you don't vectorize, a lot of the hardware just sits idle. Right? So if you don't have enough communication going on, a lot of the network hardware goes idle. Right? Now, if you write the code like this, there's a lot for the communication hardware to look at. So in particular, each of these iSends, if they're targeting different neighbors, might fire off different hardware on the, each one might hit a different communication link. And they may all then run concurrently. Whereas if you try to do them in a particular order, then you can't. The BlueJean might, depending on the size of the messages, if it only has one message to send, it might try to stripe it across multiple links, although there's a cost to that. But this makes it much easier. So this sort of deferred synchronization also gives the hardware greater opportunity to deliver data. Okay. Okay, with that, oh, I should say, yes?
What happens if you break the symmetry? So for example, if you take from one corner one of the blocks, would anything change, or this approach would still be the best?
So you mean, for example, if I put this,
remove that one, it happens, I mean, even in physical, in calculations, we might have places where it degenerates.
Right. So in that case, the communication is a little more irregular. So I should say the first thing that happens is in the original case here, if I would have gotten 4 steps, if each step was time synchronized, right? One of the things that caused problems in this case, okay, was that some of these processes got ahead of the others, right? So that's where the congestion came from, right? So if you take one of these out, you may also cause the timing of the messages to change. So that's again why doing it like this is a little better, because if the MPI implementation is sophisticated enough to respond to like back pressure on the network, I can't send any more there, and it will have something else to do. Maybe the other thing to say is that as you start taking those pieces off, then it becomes harder and harder to try to schedule around either congestion or contention. So we got congestion at the nodes. For more complex patterns, your data might have to share some of the links, and so you get contention for the link resource. And again, as you pull those pieces off and the communication becomes more complicated, those things get added. Again, the more flexibility that you give the MPI implementation for when it has to have things done, the more likely it is that the code will run well. Yes?
Yesterday also it was mentioned, and you also mentioned something along the lines that is it recommended that before posting the MPI wait all, we should do computation or not? I mean, I understand the purpose is to defer the synchronization, but is it a good practice to put computations there or not?
It depends, right? So I could give you the party line, but it's important to know that there's a difference between non-blocking and concurrent or overlapped communication and computation. So the MPI routines are non-blocking. What that means is that this iReceive completes as a call, but it does without finishing the receive. That's it. It's a semantic definition. The intent of that semantic definition is to allow the MPI implementation to move the data concurrently, so that when you do this wait all, it's done. Or maybe it has much less to do. And that certainly is a desirable choice. It's not necessarily easy to do. There are it's like everything else. Nothing is free. So on a system like BlueJean that has a fair amount of hardware to support this, if you can get the sends started, which is why you might want to do the sends and then the receives, then the hardware unit might start dispatching the data, and then you could do some computing. On a system that only checks for MPI progress, do I have something to do with respect to MPI? When you make an MPI call, then if you put computing in here, you might get all the computing done, but there may be no communication happening. And then when you do the wait all, that's the first time it notices, oh, something arrived. Now I've got to do something. In fact, you'll see some codes, and it pains me to say this, but some codes will do this computing, but then put, for example, an MPI test call every so often, which is a real hack. Here's the issue. Every time you check to see, you open the closet door to see if something arrived, you open the mailbox door to see if something arrived, That takes time, right? And if you, and the frequency at which you do that check will impact the performance of your code. So MPI implementations are stuck between a rock and a hard place. They can check all the time and then make that sort of progress. And then you do these graphs and you might see, for example, that, oh yeah, the communication happened while I was doing the computation. And it's only when you looked at the total length of time that you might discover that, well, even though everything was happening concurrently, it took longer than when I did one and then the other. And that's because you have to add in all of those checks, right? So some implementations don't check except in the MPI calls. The implementation that we did these original experiments on checked every 470 milliseconds, which is a huge amount of time, but they felt that the standard required that they do that check. So they did the check, but it was useless, right? Because it was so long. Other implementations will effectively be checking most of the time. They may, for example, they might have a separate thread that's running and watching it. Well, that's a thread that is consuming resources, right? And it's not just core resources, it's memory resources, it's bus resources, and so forth. And so everything else becomes a teeny bit slower. MPICH, for example, can be built in different modes. It can be built in a mode that has a separate thread that does this sort of progress, or not. Some implementations even had a way to turn on and off such an outside progress to tune the performance. So, I mean, this is the depends. And again, it's not that there's a right answer and people have been too lazy to do it. There really is no right answer here. There's a cost to more progress. There's a cost to not doing it, and it sort of depends on what you're doing. So again, your code needs to be flexible. For the best kind of performance, and particularly when we start talking about the non-blocking collectives, today I would probably recommend putting in an occasional call to MPI test to give that essentially for the MPI implementation to do tests, it has to go and look at the communication to see if something has arrived. You can also use iProbe sometimes. And if you do that infrequently enough, you may do it well enough to keep things going without doing too much impact. And you can imagine we've had discussions about whether there should in fact be an MPI call to do this. But now we're really getting into how do you sort of trick the implementation. You can sort of think of this, the single core equivalent of this would be a prefetch instruction. How many people know about prefetch instructions? Right. So, good. So your memory system, of course, for a lot of applications, accessing memory is what gates your performance. The memory system itself looks a lot like send and receive, right? You make a memory reference that sends a message to the memory system and says, send me this memory page, and then it comes back. And it's a non-blocking operation, so you can do other things until you need to do the wait for the memory page. Well, most systems have a prefetch instruction, which says, I am going to need this page. Right? And you can go ask it, and you can say, well, why don't I, those of you who don't know about prefetch instructions are saying, well, why don't I know about that? That sounds really cool. Because it often doesn't help, because the overhead of doing the prefetch exceeds the benefit that you get from it. You have to use them very, very carefully. There's a nice paper by Vudik et al. Where they looked at using it, and there's some useful guidance in there, but it is tricky. Right? So the same thing here with what is the right mode for MPI? Yes?
So if you were to design your MPI layer now, and with all the different interconnects around, would you choose to send large messages or smaller messages, and obviously?
So what you mean is, if I'm, so I'm designing my application to use MPI. Yep. like everything else is it depends. You can get very high bandwidth. So I would say that if it is natural to send a few large messages, that might be the best. If they get really large, then I might even pipeline them. What is true is pretty much as for everything else, the latency, the cost of sending the smallest possible message has not changed substantially in the last 10 years. Whereas the bandwidth, the rate at which you can send data has continued to go up. Right? So latency is sort of physics in a certain part of engineering. Bandwidth is just wires and signaling. And so they've been able to continue to make progress there. So a decision that was made 10 years ago to avoid sending a very long message may no longer be the right decision because the bandwidths have gone up. I think maybe that's the right way to answer your question. Okay. Anything else?